Okay, now it must be better than the previous one. Okay, right. Now, so far we know that light is traveling in a straight line. It seems to travel along straight line path in transparent medium. If it is a transparent medium, light can travel in a straight line. You have to understand this word seems, but need not be actually. There is a meaning behind that, okay? Because already we have seen that light can either travel like a wave or like a particle, isn't it? Dual in nature. But here when you are talking about transparent medium, like glass or water, we assume that light seems to travel along a straight line path. What happens when light enters from one transparent medium to another transparent medium? What does it mean? We are just taking example of two transparent mediums. For example, air is a transparent medium and water is a transparent medium. Okay. It'll be okay. Let's see. Right. Now let us see what happened. Your reactions are quite interesting. Right. Whether light is still move along a straight line path or whether it is changing its direction, because when we are talking about two different media like a transparent medium like air and a transparent medium like water or glass, if the light is traveling from one kind of transparent medium to other kind of transparent medium, is there any change in the direction of the light? Okay, that is what we have to see. To understand that, let us just see some of the day-to-day experiences, practical applications, where we can understand the change, whether the light is changing or changing its direction or not. Right. Prem, could you switch off that? It seems somewhat brighter. Yeah. Right. Now we can see clearly, don't worry. Yeah. Now for example, you would have seen a pond or a tank which is containing water, right? That water might have looked like to be raised. Have you ever seen a pond or a bucket full of water? If you just peep inside that water, the bottom of that layer, though it is very deep inside, it is not shallow, it is deep inside, but when you look from a distance, it may look as if it is shallow. That is, the bottom would have been raised, but it is not actually raised, it is very deep inside. This is one of the example. And similarly, when you take a thick glass slab, if you place it over a printed matter, for example, there is a word refraction on the paper. I am keeping that glass slab on the letter. Now you can see that the letter seems to appear somewhat raised through the glass slab. Only when you view through the glass slab, it may be looking like as if it is projected outward. It may be raised, not on the paper, it may be somewhat raised from the surface. So this is another example. And similarly, if you see a pencil which is partially immersed in a glass full of water, right? When you see from the sidewise, you can see both the diagrams here. The pencil may appear to be somewhat displaced at a interface of air and water. This is what we call as interface of air and water, because up to this water is kept, before above this air is there. So air is one medium and water is another medium, transparent medium. At this interface, you can see that it is something like it is broken. The pencil is somewhat broken. On both the diagrams you can see, right? So it is not actually, it appears to be displaced, it appears to be broken, isn't it? And similarly, another example here, when you keep a lemon inside a glass full of water, right, it may appear somewhat bigger in size than the actual size. when viewed through the sideways. For this reason, when we were children, we used to take the bulb, the organ bulb, Gund bulb. That bulb, when it is not useful, when it is fused, we used to take only the bulb and pour some water inside and use it as a magnifying lens. We used to keep that and see through that something, some letters or paper, it may look like somewhat bigger in size. Right? That is practical application of this one. So, when a lemon kept inside the water, when it is viewed through the other side, it may look as if it is somewhat bigger in size. All these examples, right? How can you give the reason for all those things? Right? For example, to understand that, let us take an example of the apparent displacement of a pencil. Right? As I said already, at this interface, the pencil is somewhat displaced. Isn't it? Now here, the light reaching you, when you are viewing from the sideways, when the light is reaching from the portion of the pencil inside the water, seems to come from a different direction compared to the part above that. That is, the light is falling on the pencil outside the tumbler, inside the water. In both the cases, the light is falling. After falling, the light has to reflect and it has to reach your eye. When it is reaching your eye, this ray is somewhat coming at a different direction, and the ray which is coming from the water after reflection, it is in a different direction. This makes the pencil appear to be displaced. It is because of the light rays coming from two different media. One is air media, another is water media. In these two media, when light travels, there is some problem. It is taking place, some phenomenon is taking place, that only making the pencil appear somewhat displaced at that interface. Right? For similar reasons only, as we have seen through the glass slab also, when you view any letter through the glass slab, it is also looking somewhat raised, because the glass slab is different media, air is different media. So the light is traveling through two different media and reaching our eye, so that the letter seems to be somewhat displaced. Now, the question is, does a pencil appear to be displaced to the same extent if instead of water we use liquid like kerosene or turpentine or some other liquid like alcohol, something like that? Similarly, will the letters appear to rise in the same height if you just use somewhat a transparent plastic slab instead of a glass slab? We are changing the material, right? Instead of changing the media, if we change the material, what we are using, instead of glass, if you use transparent plastic slab, is there any change? Definitely, you will find that the extent of effect is different. It may not be same. Whether you are using kerosene or turpentine or water, for all the three cases, the displacement will not be same. The appearance will be different for different material. Isn't it? So it means that the displacement of that object at the interface is different for different media. So from these observation that we can understand, light does not travel in the same direction in all media. This is the only point we have to understand. From all these day-to-day experiences, we understand that the light is not traveling in the same direction in all the media. That is what the inference we made from this. So, what do you understand from this? It appears that when light is traveling obliquely means at an angle, inclined, from one medium to another medium, the direction of propagation of light in the second medium changes. For example, here you take, I am using a laser light, okay, laser beam. Here there is one media, okay, and here we have got air media, glass, and this is the another screen, so that we can see the spot of light. Okay, here the screen, the glass slab. Now when the ray is passed, when the laser beam is passed through this, you can see that the direction of ray is here, somewhat here, but it seems that it is displaced inside the medium. Right? It is changing that. That too only when it is obliquely, at an angle. When you draw a perpendicular here, normal here, to this surface, it is at an angle. Say for example, it is at 30 degree for example. at 30 degree at an angle. Now the direction has to be like this only. When it is here, it should be straight away. But here what happened, inside that it seems that it is changing the direction of propagation only in the second medium, from the first medium to second medium. And this phenomenon is nothing but called a refraction of light. So when definition is asked, what is refraction means, what you have to say, when light ray is traveling obliquely from one medium to another medium, the direction of propagation of light in the second medium changes. This phenomenon is known as refraction of light. Or simply, in a nutshell, we can say the bending of light ray. The bending of light ray when it travels from one medium to another medium is called a refraction of light. So this is what refraction. Okay. Now you can understand that only when it is traveling in the medium, only when it is traveling in a transparent medium, it is a transparent medium. Suppose in place of this, if you keep a mirror, like as you asked in the beginning, if you keep a concave mirror or convex mirror, do you think that light will pass through the glass surface? It cannot, because it will simply reflect back. So to refraction to take place, the medium should be a transparent one. The medium should be a transparent one. But mirror is not a transparent, it is a reflecting surface. So in mirror, the refraction cannot take place. Okay. So that is the point you asked us. It is clear now, I think. Now, let us understand the same phenomenon of refraction by doing another activity. There is a small activity given in your textbook, for which you are going to place a coin at the bottom of a tumbler or bucket, say bucket of water. Okay, at the bottom of the bucket, you are going to place the coin. Right. Now, by looking at the side of the bucket or tumbler, it may be a bucket because you are going to keep the hand inside and take the coin. Okay, you are going to pick up the coin inside in one go. That means you are not peeping through this. You are going to see through the sideways so that the coin can be seen, and you are going to keep inside the bucket and try to take the coin at one go. That means only one trial. Do you think that you can do that? Do you think that you can do that? Exactly, you can pick up the coin easily? No, it's only shallow, somewhat little water only. The bucket is easy to take. But the question is, the coin is kept inside the water. Okay, only this much of hand will be wet when you keep inside. But doesn't matter, it's only easy task only. But the coin is here only at the center, for example, or somewhere here. What you are going to see by looking at the coin through this transparent medium. Okay, you can see that through that, and you have to keep that hand inside and take the coin. Now the question is whether it is easy or not. At one trial, can you do that? Why? Why is it so difficult? No, that is not. Yeah, that is the point. The coin, whether it is deep inside or somewhere, that is not a problem. Why it is difficult? Because the position of the coin, when it is seen through the water, okay, when it is seen through the water, will be different from the actual position. You may think that the coin is here. When you keep inside, the coin will be somewhat displaced. When you put inside the hand only, you will understand that the coin is not in that position. Because it is, the light is traveling in different direction. When it is traveling from water, right, it may be actual. But after coming out, it is traveling in the air. So that the position will be displaced. So that you will find it very difficult to locate the coin with one trial. You can just try with friends also. They will also struggle to pick up the coin in one trial. That is what says about the displacement of any object when it is kept in different media. Okay, right. That is another interesting experiment. Right. This experiment will help you to understand the phenomenon of refraction by using a glass slab. Okay, Now let us see. Refraction of light through a prism. Okay. Just hold for a moment. So in this video, it's like a lab experiment through which we are going to learn about the refraction of light using a glass slab. We know that glass slab is a different media, isn't it? Glass slab is made up of glass, and outside the glass it is only air. Now we are going to perform the same activity by using, let us see. Just a moment. Yeah, now I'll play.
Let us observe an experiment to trace the path of the ray of light passing through a rectangular glass slab. So we've taken a rectangular glass slab and we placed it on a white sheet. Then almost through the center of the glass slab, we point that mark and we draw a normal. So we observe that we've drawn a normal. After that, we also draw the outline of the glass slab. This is the arrangement that will be observed. Then, with the help of a protractor, we will mark approximately 30-degree angle from the normal and join it to the normal and the boundary of the glass slab. On this line, we are going to place two metal pins, which will be placed approximately 6 centimeters apart. We should take care that the pin should not be bent, it should be straight pin. So one pin I will join here, and the other one would be placed here on the wooden board. Once the pins are fixed, just remove them and make a circle to highlight their position. Now we have to observe these two pins through the glass slab. To do so, you have to bend a little and observe the position of the pins. Wherever the images of these two pins will fall, you will have to place a third metal pin after the images of these two pins. So I have put the third metal pin here. Similarly, we will take another metal pin and we would be placing this metal pin after I observe the images of these two pins and the position of the third pin. slab is that all these pins are aligning in the same line. Once I place the two metal pins, I remove them and mark their position. These two positions are marked, and simply now we will join these two positions with the boundary of the glass slab. The line is a straight line, and if we measure the angle that is being subtended by this line, we observe that the angle is equal to approximately 30 degrees angle. Therefore, this is our angle of incidence, angle I, and this is angle of emergence, angle E. Now, if we extend the line, the normal here, if I extend the normal here and I join the two lines, I see that I get a bend line. This is the angle of refraction that is formed. This is the angle of refraction, and if we further, you can mark it as angle R. If we further extend this line, that is the line of incidence, we get a parallel line of emergence and a parallel line of the incident ray. Now the perpendicular distance between the incident ray and the emergent ray is known as the lateral displacement. Therefore, due to the difference in the density, air and of glass, the light ray was bent, it got reflected, and it emerged outside the glass slab. So there are four observations that we can make here. The angle of incidence, the angle of emergence, and the normal, they lie in the same plane. The angle of incidence is equal to the angle of emergence. And if we extend the incident ray and we compare it with the emergent ray, both of them are parallel to each other, and the perpendicular distance is the lateral displacement which has happened due to the surface of the glass slab.
So now this small experiment will explain how the light beam, when it is traveling from one medium to another medium, why it is getting displaced, right? It is the fact that later we will understand that the light will be traveling with a different speed in different media. When it is traveling in air media, the speed will be different. When it is traveling in a glass or something like water, the speed will be different. Due to that, the direction is somewhat displaced. The direction is displaced. Due to that only, instead of, if it is, suppose if the incident angle is in one direction, the light has to travel in the same direction. But when it is coming out of the glass slab, you would have seen that it has got some laterally displaced to some other distance. It is because of the fact that the refraction of light in the different medium. You can watch another interesting experiment which will explain about the refraction through a glass slab using laser beam. This will be somewhat interesting to note. Because using ray diagram, earlier we have explained. Now here you can see that this is explained using a. Sorry. Take another. Yeah, this one. Yeah, you can notice that this is somewhat different.
Light travels in straight lines. Shining a powerful light source through a thin slit produces a straight, narrow beam. Place a glass block in its path and the beam starts to behave differently as the block is rotated. Some of the light is reflected, the rest passes into the glass. The light bends in one direction as it enters the block and in the other as it emerges from the lower edge. This shift in direction is called refraction. To work out what's happening, think of light as a series of waves. This ripple tank uses a dipper to send parallel water waves across its surface. Putting a plastic sheet into the water makes this part of the tank shallower than the rest. Waves travel more slowly in shallow water. This change in speed changes the wavelength. The wavelength on the top is shorter than the one on the bottom. When the sheet is at an angle, the waves also change direction. The wave fronts bend as they reach the plastic sheet. To understand how speed can cause a change of direction, imagine a truck approaching marshy ground. If the marsh is at an angle, the right wheel slows first. The left carries on its speed for longer, swinging the truck round. So when light hits a glass block, it changes direction because it changes speed. Place a glass trough in the beam, and you can see how water also affects the path of light. The bending of light helps explain why this apparently straight stick is in fact bent. While this bent stick is actually straight. Refraction tricks our eyes, making us think that the stick is nearer the surface than it actually is. These gannets have to take this into account when they're diving for their underwater prey. Pass a ray of light through a semicircular glass block, and again it's both reflected and refracted. This happens at the straight edge. As the block is rotated, the angle at which the refracted ray leaves the block changes. Eventually there's no refracted light. Instead, all the incident light is reflected back inside the block. This is known as total internal reflection. At a certain angle, the light stays inside this plastic rod. Total internal reflection allows light to travel through a curved shape. A laser beam can even be made to travel along a curved stream of water. Optical fibers work by the total internal reflection of light. As well as being decorative, they also have practical uses. Telecommunications rely on total internal reflection to transport information along cables underground.
Right. Now we have seen that for every angle of incidence, the ray is refracted at a different angle, right? So all these experiment shows that the light, when it is traveling from one medium to another medium, it is getting refracted. But in the previous video you have seen, at one particular angle there is no refraction taking place. Because in every refraction part of the light is reflected and part of the light is only refracted through the glass prism. But there is one angle, what we call as critical angle. At that particular angle, right, the total light will be reflected back, not refracted. It is totally reflected back. That is called a total internal reflection. You will study about this total internal reflection in 12th standard, because this total internal reflection is only made use of in optical fiber cable, we call OFC, which is used for telephone lines. In the roadside you have seen, they used to lay the telephone cables, pipe like. right? Different color pipe, blue color, orange color, like that. So those cables are nothing but optical fiber cable. And also you would have seen a flower was decorated here with the light, which is also called a optic fiber. And these optical fiber, they are designed in such a way that when light is passed through that, the light is allowed to get internally reflected, no refraction taking place. It is totally internally reflected so that it can reach without any loss. So that concept only made use in the optical fiber cable. Now in the previous experiment with the glass lab, you would have seen that, or in the next video also you would have seen that the refraction which is taking place in different media, it is only because of change in the speed. As rightly pointed out in the video, when the truck is traveling from a concrete road to the marsh road where the soil is very, very loose, so the tire gets stuck at one side and it is changing the direction. In the same way, when the light is traveling from one medium to another medium, the speed of light is changing. Right? It is because of this change in the speed only, the direction of light is also changing. Right? And these experiments show that the refraction of light occurs according to certain laws. Right? They framed the law by looking at the observation. From the observation they have inferred and they framed two laws which are called laws of refraction. Let us see the first law. The incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. It is similar to the laws of reflection. Right? What is that here? The incident ray, right? The refracted ray. This is refracted ray, right? And the normal. This is the point of surface, right? This is the point where it is dividing the media. This is called a plane, right? In this plane there is a normal to that plane at that point of incidence. All these things are lying in the same plane. Which plane is that? You can see that if you consider this as the plane, right? This is the plane, for example. I have taken this as the plane. If we take this as a plane, right, and this is the medium and this is air medium. Now the light is traveling, right, on this plane, for example. On the sheet, I am drawing line like this, like what we have done in the glass lab in the experiment. So the incident ray, the refracted ray, and the normal to the surface, interface. So all these three, they lie on the same plane. So this is what we call as the first law of refraction. And remember, the word you have to remember, in the laws of reflection we use reflected ray, the incident ray, reflected ray, and the normal to the surface. But here the word refracted ray and the normal to the interface of two transparent media, they lie in the same plane. That is the first law. The second law says the ratio of sine of angle of incidence. The ratio of sine of angle of incidence to the sine of angle of refraction. Okay, sine I by sine R. Sine I means sine of ratio of sine of angle of incidence to the sine of angle of refraction for a given color or for a given medium. Okay, for a given pair of media we say, whether it is water and air or glass and air or glass and water, whatever the pair of media we take, for these two pair of media, the ratio is a constant. The ratio is a constant. Suppose if I change the angle of incidence, accordingly the angle of refraction will change so that the value will be remaining same. That is what it says. Right? So sin I by sin R will always be a constant. And this law is which is called a Snell's law, which is given by the great scientist Snell. So it is named after him. So this is called a Snell's law. Sometimes they may ask, state the second law of refraction, or they may ask, state the Snell's law of refraction, or state Snell's law simply. So you have to remember that this is what the Snell's law. If you remember this formula, straight away you can put it in a sentence. And this constant value, right, what we call it as constant here, this constant has been given a special name, what we call as refractive index. Okay, we call it as refractive index. But since we are using two media, we say the refractive index of the second medium with respect to the first one. Refractive index of the second medium with respect to this first one. So that is what the constant is otherwise called. Okay, these are called the laws of refraction. Now we said that refractive index, isn't it? So what is that actually? We'll see. Now, so far we have understood when light is traveling at an angle obliquely from one medium to another medium, it is changing the direction in the second medium only, you have to remember, right? It is changing the direction in the second medium. And this extent, how much it is changing the direction, it is taking place in a given pair of media that is expressed in terms of refractive index. So, by using that constant value, refractive index value, we can say whether the medium is denser medium or rarer medium, okay, with respect to the light, okay, based on the refractive index only we can say. Or by using the media we can say whether the refractive index is how much is that. So by using that only they will design the optical fiber cable, all those things. Okay, right. Now the refractive index can be linked to the relative speed of propagation of light, because we can understand by using what kind of index, what number we are taking, so that we can calculate the speed of light in the particular media, because we have understood that light is traveling with a different speed in different media. But usually we know that the fastest medium is the vacuum or the air, we say. Generally we say the air, that is the vacuum, is the media where the light can travel at the maximum speed. We know that 3 into 10 power 8 meter per second is the velocity or speed of light in vacuum. Or otherwise in terms of kilometer, can you tell me in terms of kilometer how much is the speed? How much is that then? It will be quite astonishing that light is traveling with a speed of 5 lakh kilometers per second. In 1 second, light is traveling 3 lakh kilometers. If you take 3 zeros here, it is 10 power 5. 10 power 5 is nothing but 1 lakh. 3 into 1 lakh is 3 lakh. So in 1 second, just if you give 1 second, it can travel 5 lakh kilometers. That much speed the light can travel in vacuum, right? And this speed will considerably change in different media like glass or water. Okay, it may be changing because the glass or water, when you compare with the vacuum, it is somewhat denser. So when it is denser means the speed naturally will be reducing, right? It is like a crowded area. If you are trying to move, your speed will get reduced. In the similar way, the light speed will considerably be reduced in different media like glass or water, right? So the value of this refractive index for a given pair of media depend upon speed of light in the two media. Okay, for that they have given one a tabular column in which you will understand that how the refractive index is changing. So here there is a simple information given here to understand that. Say for example, let us consider a ray of light which is traveling from one medium to another medium. Say we take this air as the first medium and say glass is the second medium. Okay, right? And we know that the I is the angle of incidence and R is the angle of refraction. Okay, so these are the two information we have to take for consideration. Now, since we have taken two media, in the first media, let us take the speed of light as V1 and V2 as the speed of light in the second medium. Okay. Now, what is that refractive index is? It is nothing but we are comparing the speed of light in two different media. Okay. So, the refractive index of the medium 2 with respect to the first medium is nothing but given by the speed of light in the first medium to the speed of light in the second medium. Ratio of speed of light in the first medium to the speed of light in the second medium. And it is usually expressed as n21. n21 because we are giving the ratio of second one with respect to. So what is importance given means second medium. So when you take the first medium and second medium, we are talking about the refractive index of the second medium because say for example glass means here we are talking about the refractive index of the glass. But with which one we are comparing? We are comparing with the air. So refractive index of the glass with respect to air. So N21. It is usually N21 or we call it as mu. What do you call it as? Mu. So we call it as mu. Okay? Mu 21. Mu, like a cat we have to mu 21. So speed of light in medium 1 by speed of light in medium 2, it is V1 by V2. Okay, so in terms of speed only, here we are expressing the refractive index. Okay, right. Now similarly, when you are comparing other medium, say for example, refractive index of the first medium with respect to second medium. Say for example, if you are using water and glass slab. Okay, so that also can be represented as nu12 or n12, which is v2 by v1. Only the velocity will be changed. Okay, if the medium is, say for example, vacuum or air, right? Suppose if the we are taking one medium, right? One medium air or vacuum with respect to the other medium. So that is called the absolute refractive index of the medium. When you are comparing the refractive index of any medium with respect to air or vacuum, that is called the absolute refractive index. It is simply represented as N2. Right? N2 means the second medium is compared with the air or vacuum. Okay, simply we say, when you say refractive index of any medium, doesn't mean, it means that we are comparing the air media or vacuum. Okay, so hereafter we will see simply N2, not N2 or N12, we say simply nu or nu2. That means we are specifying the refractive index of that particular medium with respect to the air. Say for example, if C is the velocity of light, we have taken air medium or vacuum. Generally we say air is the comparison. So we are comparing the speed of light in air with the speed of light in medium. So what is that? C by V. It is nothing but C by V. So nu is nothing but given by the refractive index of the medium is given by C by V. Simply we can say C by V. If it is two different media means we will say V1 by V2. Here we are talking about air, it should be written as C by V. So what is refractive index? It is absolute refractive index of the medium. Whatever we call it as, here nothing but absolute refractive index, or otherwise simply called a refractive index. Here in the textbook you would have seen that there is table given, tabular column. Okay, the tabular column will give you the different refractive index of materials, different materials. For example, if you take water, for water the refractive index is 1.33. That means the ratio of speed of light in air and the speed of light in water is 1.33. What is that? 1.33. Here the value, here for water the value is 1.33. What does it mean? If that value is more than 1, what do you understand from this term? If it is 1.33, whether this is greater or this is greater. Air only, because since we are talking about water, if the value is greater than 1, it means that the speed of light in water is lesser, in air is more. So when the light travels in water, the speed is reduced. So when you are comparing that, we are getting the value as 1.33, right? Similarly, there is a big tabular column given. You can just look at that. There are different values given here, for which you need not memorize at all, but just as you have to observe that which medium is giving out greater refractive index, which is lesser, like that you can compare. So for air only it is 1.003. Actually it is 1. It is considered to be 1 because we are comparing the refractive index of air with the refractive index of, that is speed of light in air with the air. It means naturally it will be C by C, it is 1. isn't it? So it is 1. So and similarly for ice, water, alcohol, kerosene, all these materials are given. Usually the basic things we have to remember. Exactly, water is a usual one which we use in our daily life. So the refractive index of water is 1.33. That you have to remember because sometimes in the exams they may ask. So water, for water we have to remember it is 1.33. For air we have to remember 1.003. And apart from this, you can, the other things are different here. For example, the crown glass here. The crown glass is the one which is used for making prism, glass prisms, which we use in the laboratory, school laboratory. Okay. So all these things are only for reference. You need not memorize at all. Okay. So just remember this air, if at all ice, because ice is very closer. It is 1.33, 1.31. Okay. These two you can compare. Okay. And kerosene also 1.44. Now you compare this. Can you tell me what do you infer from these two values? Water and kerosene. Water and kerosene. Whether the density of water is higher or density of kerosene is higher. Quickly. I am asking about the mass density. Mass, when you are comparing the mass density of water and mass density of kerosene, which one is higher, which one is lower? Tell me. Which one is higher, which one is lower? No, you are wrong. No, you are wrong. I am not talking about this value. This is refractive index. I am not talking about refractive index. I am asking you to tell me, when you compare kerosene and water, which one has got more density? If you pour kerosene in water, do you think that kerosene will float or water will float above? Pardon? Huh? I didn't understand. What is that? You are using kerosene. You are using kerosene water. You are mixing it, right? Which one will float? Thinking, oh my God, have you ever seen that? It's very usual one, you know. Even in seas also, the ships which are carrying oil, right? Ships which are carrying oil, petroleum oil or crude oil, when it got bursted out, when it is filling on the water, you would have seen that the oil may be floating on the water, usually. Similarly, kerosene also, it is mass density is very less, very light you can say. When you compare water and kerosene, the kerosene has got less density, water has got more density. So when you pour kerosene and water together, we call it as cannot be mixed together, isn't it? So the kerosene will be floating on the water because it has got less density. But since it has got less density, it doesn't mean that the refractive index will be lesser. Though it has got less density, you compare the refractive index, it is 1.44. Here it is 1.33, here it is 1.44. So what do you understand from these two terms? The refractive index of water is 1.33, refractive index of kerosene is 1.44. With these 2 points, think about it. compare with the mass density and refractive index. Okay. Why? When density of kerosene is lesser, the light should travel faster, When light is traveling faster, the refractive index should be lesser. But here it is more than the water. Okay. I leave this question to you. Think it over and answer this question in the next class. Why is it so? Alright. With this, we'll wind off. Thank you.